complex procedure, and we'll see in a bit. So we're going to kind of view it as adversarial because that's like an easy way to make progress. Okay. So it'll be more in the second theme. So let's get right into the problem of interest. So we have a PSD matrix A. It's an n by n matrix, and we want to just estimate the top eigenvector. Okay, so essentially what it is right, if you have a bunch of data, the top eigenvector is roughly like kind of where the data is pointing to in the most. Okay, here A would be the grand matrix of the points, but just imagine data. You want to find the direction that data is pointing to. So more formally, if I let V star be the top eigenvector, right, it realizes this maximum eigenvalue. I don't want to approximate the vector in some sense, but I want to output another vector that's close in value. Okay, so given some parameter epsilon, I want to output a unit vector V such that V transpose AV is 1 minus epsilon times lambda 1. Okay, so that's the problem. Any questions so far? Okay, so eigenvalue. So okay, eigenvector. So I haven't talked about adversarial stuff yet, so I need to talk about first. I need to talk about the power method, the real MVP. So the power method is a really generic and flexible tool for finding the top eigenvector. So what you do is you start with some vector v, and you keep multiplying v by a over and over again. And at every intermediate step, you normalize, and you keep following this loop. And essentially what happens is if you start with a good enough initial vector v, you'll keep your approximation unit vector v will start aligning more and more with the top eigenvector. Okay. And this is called the matrix vector product. It's in this model called matrix vector products, where essentially the only way you look at the matrix A is using matrix, right? So it's a MVP. Okay. Anyways, so to be more precise, let v sub t be the vector that we have at time t. How you start power method is the vector v sub 1 should have some non-trivial correlation with the top eigenvector. Let's say correlation 1 over poly n, and then you just do this loop like some number of times. The question is how many times? To do that, let me introduce the standard way power method is analyzed. So for simplicity, let's just say A is like a really nice diagonal matrix where the top eigenvalue is 1. The other one is 1 minus 2 epsilon, right? This is not exactly 1 minus epsilon approximation, so I really need to get closer to the 1. Okay. So if I let v sub t be the normalized vector at time t, right? My approximation in this loop, then I can write this vector as, it has some component in the top eigenvector and some component in the rest. And I'm going to let C sub 1 be the component that I care about, which is the component in the top. And C sub 2 be like sort of the eigenvector, the vector mass in the other direction that I don't care about. And kind of, if you look at how power method is analyzed, essentially we use this quantity to track progress. So why is that, right? So if I say, okay, at some point V, at some iteration T, right, what is the progress I've made? Well, you can just, compute V transpose AV at some point T, okay? And you notice, right, like because, right, it's a diagonal matrix and whatever, and these are eigenvectors, let's say, the only thing that pop up are the squared part of the masses. So essentially, right, I can just forget about things in the second eigenvector and just say, okay. So what that means is really, right, if I have, let's say, very, very high mass in the top direction, then I will actually have a good approximation to the eigenvalue. Okay. So this is all sort of standard power method analysis. I'm just saying that we use the mass in the first coordinate as a way to keep track of progress. So let me just show you the quick analysis, or like a rough analysis. And the reason I'm doing this is like I'll contrast it with this adversarial setting that I'll show in a bit. But right, one way to measure progress is let's just compute the ratio of the of the mass in the bad directions over the mass in the good direction. And it's roughly we want this ratio to be decreasing, right? Because V is a unit vector. So if this ratio is decreasing, then it's intuitively saying that the mass in the right direction is increasing, which is what we care about. And right, the analysis is very clean, right? So right here, I'm assuming the top eigenvalue is 1. So the mass in the first direction at time step t, it's just the same, it doesn't change. But the mass in this other direction gets multiplied by 1 minus 2 epsilon. And it's nice to actually look at this ratio. So when you do power method, right, there's this normalization step, but you don't really care about the normalization step because somehow the ratio kind of kills the normalization. Okay, so it's very nice. And right, you can imagine, right, after t steps, right, the bad directions keep accumulating this, smaller than 1 factor. So after t steps, this ratio is roughly like this. So it kind of says, okay, if I take t to be roughly 1 over epsilon times some log factors, right? Then, right, I want to make this ratio, maybe a very, very small number, right? So I need to take t to be roughly 1 over epsilon, right? To kill this, right? Okay. All right, so that's like, the entire analysis of power method. You need 1 over epsilon steps of exact matrix vector products, okay? If you have a nice PhD matrix. Okay. And like I said, in the standard analysis, this ratio is key to measuring progress. All right, so this is like a crash course in linear algebra. So now let me talk about our adversarial setting. Okay, oops. So first, let me give you the definition, and then I'll tell you where it comes from much later. But this is not a model that I just, we just came up with. This was like embedded in some algorithms problem that we're working on. So instead of getting exact matrix vector products now, I get approximation, right? So I give you a vector v to someone in the sky, and they send me a v plus e, okay, some error. And I don't have any control of the error, except they're constrained to only have, the norm of the error has to be sort of proportional to the size of the answer, okay? And in our setting, what it was that if you spend a little bit more time, you could get much, much better approximation. So roughly, right, if you spend time that scales with 1 over delta squared, then you can make delta smaller and smaller. Okay, so that was our setting. Yeah.
In this model, can you spend some amount of time getting the exact answer, or always?
You can spend, let's say, n squared time getting the exact answer. Yeah. But that's not really nice, right? Like, well, anyway, we'll see later. So essentially, what's happening is, I have a vector v, right? A times v like stretches it in some direction, but maybe I get the green arrow because like the adversary says, okay, and I'm gonna move it a little bit, okay? And the question is, can I use this to approximate the top eigenvector now, or the top eigenvalue, 1 minus epsilon approximation? This is not yet interesting, right? This is not yet an interesting model because, right, the way I said how power method works is initially the first vector has very, very small correlation. So even in the very first step, right, if delta, you think of like a small constant, they can just kill, if the correlation was 1 over poly n in the beginning and delta is a constant, kind of makes sense that they can just kill the progress in the first direction in the very first iteration. And like, you don't even have any, you don't have any representative in the first direction, right? You're like totally unaware of it. So this is not an interesting model yet. Like this won't help you. But it turns out in our setting, we could also guarantee something nice. If I just assume V star is a unique top eigenvector, it was also true that the error has the inner product of the error and the top eigenvector was always non-negative. So what that intuitively means is that the adversary can manipulate the error in every other direction, but they cannot touch the top direction, right? So it kind of preserves some notion of progress. Okay, so this was our adversarial model. And let me tell you like how the adversary can intuitively mess you up when you're doing this power method loop. Essentially, by adding more mass in the irrelevant direction, they can hurt you because, right, you have to normalize, right? This vector v has to be a unit vector every time step. So if I add a lot of mass in the other direction and I normalize, that's intuitively taking away mass in the first direction. Okay, so that's kind of what's happening. So where is this model coming from? Like, maybe it's a natural model, but it was, like I said, it was embedded. We were working on some other problem, and somehow this model was there. And right, we had an algorithm that could roughly guarantee this for an interesting matrix, but there's no way we could analyze what the hell was happening. It was like a very, not complicated, but it was an involved algorithm. So like, who knows how this error is generated? We just had these guarantees. So we said, okay, it's an adversarial process.
Doesn't it also come up in differential privacy and like noisy power method?
Yeah, it does. So the one difference here is like in these noisy power method things, essentially the error is random, or in DP the error is random. Here the error could not be random, but somehow this also, the error is like whatever, it just satisfies this.
But they have like force bounds with adversarial, maybe.
Essentially for these things, for those random cases, you need delta scales like 1 over root n. Here delta can be whatever, right? It's a parameter of the problem, right? If you have delta 1 over root n, then it kind of doesn't make sense in our setting anymore.
Are you also needing some relation between the gap?
No, there's no relation between the gap. Okay, so the problem is as follows. Now let me tell you the problem, which is I have access to this oracle. I can set delta, but pay a higher running time. But I want a 1 minus epsilon approximation of lambda 1. And the question is, does power methods still work in some sense? Did I write that down? Oh yeah, yep. Okay, so right, so I'm gonna call this a delta MVP. Doesn't really matter what the running time is. I just wanted to show you that we had the power to set delta, but ideally, right, I want to set delta as large as possible because I pay in the running time. But right, epsilon still is the major input of the problem, and I want to output a vector v that witnesses like a 1 minus epsilon times lambda 1. Okay. So there's two questions, right? How do I appropriately set delta? Of course, if I let delta go to 0, then it makes sense like, okay, at some point power method will start working, right? If I let delta be 0, for instance, right, you get exact MVP. And also, right, how do we analyze power method with this noisy or adversarial or whatever? Okay, so let's go back to the standard analysis. Yeah, sorry.
Does your model or analysis, does it help to use different deltas as you go on?
No. We'll see later. Yeah, that doesn't help. So right, like I said, right, let's say our matrix is this nice matrix. So right, the way we measure progress in power method was we wrote, at iteration t, we wrote the vector as a component in the top direction and the other component, and we looked at these coordinates, right? The mass in every in the right directions. And the lesson from standard analysis was like somehow, right, the clean way to do power method analysis, you really look at the ratio in some sense, and you say, okay, as long as the ratio is decreasing, you're making progress. So so now let's see what happens if we try to put it in this or use this adversarial or noisy matrix vector power. Well, okay, so like I said, right, the adversary cannot mess with the first direction, so somehow the mass in the first direction doesn't change, and the eigenvalue is 1, so it's the same thing. But what the adversary can do, for example, is put all the delta mass that they can control in the second direction, right? So we want this ratio to be decreasing, but somehow the adversary is boosting it a little bit. Well, we want it to be decreasing. The denominator is not changing. So essentially, it's like a simple linear inequality, right? Like if I want the ratio to be decreasing, then I get this relationship. I can subtract things. So essentially, that means that sets a constraint on how large delta can be. So delta has to be smaller than epsilon times C2, okay, which is the component in the bad direction. But at some point in a power method analysis, C2 will be very small, right? Right? If you do it in the standard way, at some point it'll be roughly like square root of epsilon. Because, right, like I said, I want this C1 squared to be 1 minus epsilon. So at some point, C2 squared will be epsilon. So that really means delta, if you do the standard analysis, delta has to be epsilon to the 1.5. Okay. So why is that a little bit weird, right? Like, so first when we did this, that was really weird because somehow, right, I want to get epsilon close to the top the eigenvector. So it seems like if I just have epsilon approximate MVP, I should be able to do it. Not epsilon to the 1.5, right? Like remember, epsilon is a small number, so this is a much smaller value than epsilon. Right, so this is like an undesirable, not aesthetically pleasing, right? Somehow the right parameter should be epsilon because that's kind of the precision that we're asking for. But if you do the standard analysis, it gives you something a little bit worse. Okay, so let's try to improve it. Yeah, so essentially the question is, right, in this framework or in this setup, what is the largest delta that we can get away with, right? Because if delta is large, then we don't have to pay in the running time. And it's just like an interesting question itself, like, what is the largest amount of noise we can tolerate in the power method if I have this epsilon be fixed? Okay, so the problem with standard analysis is it kind of ignores contributions from the smaller the eigenvalues, right? All I said was like, well, I just need to keep track of the power, the mass in the first direction, and I really didn't care about what happened in the other directions because the way power method works is like really kills all the mass in the other directions very, very fast. But it turns out we can be a little bit smarter and say, okay, you know what? Let's just get some help from the other direction too. Why not? So for example, in this thing, right? Take this vector v, which is just the uniform mass in both coordinates. No way, this coordinate is not close to 1 minus epsilon, right? It's a constant. It's not close to 1, but it is good enough in this case, right? Okay, because I'm gonna, for this specific example, I'm gonna also keep, I'm also gonna say, okay, you can help me too. Right. Previously, I said, okay, I only look at the first direction, but now let me also look at the second direction, because it's not like I want to approximate the top eigenvector exactly. I just want a vector that has high, high V transpose AB, right? Like witnesses the eigenvalue. So that's a little bit of a different problem, right? So that's the main idea, which is okay. Let's just let's also use the other eigenvalues to help us. And like I said, we're going to track progress in a slightly different way than just saying, okay, make the mass in the first direction large. We're going to intuitively keep track of all the eigenvalues together. And just a note that, like, you might say, okay, why doesn't this help the standard, power method matrix vector product analysis? It actually doesn't. Like, it doesn't give you a better bound on the number of steps. Like, there's another example of a matrix A where power method would still take 1 over epsilon steps. Okay?
But there are like Krylov methods.
Yeah, so we'll talk about that in a bit. Yeah, talk about power method. All right, so let's remind everyone of our setting, right? We, every time we ask for A times B, we get a noisy answer or an adversarial answer. The adversary can do whatever they want up to some bounded radius. And I'm also promised that they cannot mess up progress in the first direction. All right, but they can, intuitively boost progress in the other directions. Yeah, okay. So our goal is to say, okay, intuitively, right, setting delta equals epsilon should be the right answer. So we're going to try to do that. And the idea is very clean. So before we get here, right, we had a very complicated proof that was like tracking eigenvalues at every scale, like very precisely. It was like a very complex dynamics. And then we woke up one day and we said, okay, we can just change one line in the power method analysis. And that was a very, very nice feeling. Okay. So, right, previously, what power method did was that, okay, at every step, the mass in the first direction will increase by a multiplier factor. That's essentially what power method was doing. Okay. But now we're going to say, okay, we're going to add another condition. Either this happens or we're already at a good answer. Okay, so that's the only change. And so what that means is we actually cannot just take a bunch of iterations and stop. We have to take the best vector found at all iterations. So that's the one change that we have to make. But essentially, that's the only thing. Like either the power method work or you are already done. Okay, in this adversarial or noisy setting. So, right, like I said, the first step is enough, right? You don't need to include this second step in the standard analysis. In the standard analysis, it was always the case that the first component was increasing no matter what. Every step was increasing by a multiplier factor. So if we prove something like this, then we're kind of done, right? Because the first direction can't really increase too many times, right? It's a unit vector, right? It starts with some non-trivial value, like 1 over square root of n or 1 over poly n. It increases multiplicatively. Well, that can't happen, right? It has bounded by 1. So if we show this claim, either this happens or this happens, then we're kind of done because it shows, okay, if I set delta equals O of epsilon, then power method will still take 1 over epsilon steps. And will give me 1 minus epsilon approximation to lambda 1. Okay, so the main goal is to show these two things. Like I said, so I wrote it either we're making progress or we're already done. Okay, so that's like the simple change. So how do we show this? So this might be a little bit like math heavy, but sorry about that. So right, what is the progress? What is the mass in the top direction at time t plus 1? Well, I take the inner product with the top direction, right? That's by definition. Now, what is this vector, right? Well, it's actually a normalized vector, right? I did power method and I normalized it, so it's actually a normalized vector. So this vector v tilde is the vector I had before I normalized it. Okay, so that's everything is exact so far, right? This is just what our method is doing. And now, what was this unnormalized vector, right? Well, it was the result of a noisy or adversarial matrix vector product, right? This unnormalized vector was where I took the vector at the previous time step and I added some error, right? And I keep, I'm going to keep the normalization. So that's going to be the key thing. I'm going to keep track of the normalization this time. Whereas previously in power method, right, I didn't care about normalization. It was kind of canceled on its own. But here I have to care about normalization a little bit. And of course, like I said, the adversary cannot, hurt me in the top direction. So I still get this lambda 1. This v star dot e is non-negative, so I can just drop it. Okay, so I just get this lambda 1. And of course, I'm going to keep track of this normalization. Okay, so far it's sort of like exact analysis in some sense. I'm just like following it very closely. And now this is where the second part comes in, right? So I'm going to assume, okay, we're not already done, okay? So that's so it's wrapped in a contradiction. So what does that mean, right? Well, the norm of the matrix vector product, the noisy or the adversarial matrix vector product, is at most 1 plus delta times the norm of the thing, right? That's my constraint, right? The adversary can only move me in a delta direction somewhere, like with bounded delta norm. So that's true. I haven't said anything smart yet. And then kind of maybe like the one more step beyond that is, well, if this thing, right, this is wrapped in a contradiction, right? Which is, I'm assuming this thing is small at all time steps. So if this thing is small, it turns out it's also, there's like one more step that I'm not sure, but it's also almost equivalent to showing that this thing is small. Right, this thing is not exactly this thing. There's like an extra a squared here, but turns out it's the same thing. You can factor out lambda 1. So if this thing is small, like, if I say, okay, if I assume that this, B transpose AB at some time step is smaller than 1 minus epsilon lambda 1, which is bad, then it turns out this is also small by the same amount, roughly. And now, right now, it's clear. Now I set delta to be, let's say, epsilon over 100. And now this denominator is smaller than 1 minus epsilon over 2 times lambda 1. Okay.
That should be 1 plus delta.
Oh yeah, sorry. 1 plus delta, right? Yeah. So if I said 1 plus delta and then delta is epsilon over 100, right? There's a plus epsilon over 100 and a minus epsilon. So they combine to be, let's say, minus epsilon over 2. Okay. So,
sorry to do this because I came in late, but why is E dot D star non-negative?
that's part of the model definition. Okay, that's part of the model, yeah. So if it's not, then like this model doesn't even make sense because they can kill the progress in the first iteration already. Okay. So yeah, sorry, it's B plus. Okay, but like, okay, now what happened, right? I mean, just like plug it in, things cancel, and look, this is growing by 1 plus epsilon factor. So somehow, like, we didn't really do anything, but just by changing this one step, we got this nice behavior, which is either we're already done or we made progress like before. So that's it. Okay, that's the end of the proof. Okay, so it's previously it was like a very messy proof, but now somehow, right, what happened here was by keeping track of the normalization, okay, it's kind of intuitively tracking all the eigenvalues at once. So that's kind of what's going on. Okay, so what is the final guarantee, right? If I have this delta MVP model, right, where the adversary or whoever, noise adversary, whatever, if they can move my error, my vector in a small radius, but I'm guaranteed that they cannot kill progress in the first direction, then power method still works with sort of the, the natural setting of delta is epsilon, and it still takes the same number of steps. Okay, 1 epsilon. It doesn't get any slower. All right, so now let me just give you a quick peek of where this model came from. Like, it's not like we sat down in a room one day and said, okay, I really want to study adversarial power method, which is a very valid thing to do, by the way. It's a very interesting question, but it was like, okay, we're working on another problem. So the problem we're working on was, it's not relevant to the rest of the talk, but I thought I'll show you where it comes from. I have some points, and I want to find 1 minus epsilon approximation or whatever, to the top eigenvalue of an interesting matrix. So the matrix is every ijth entry is like some Hurdle function. And really, like, the theorem that we had was, okay, you could do this in time that's roughly n over epsilon cubed. Okay. And our improved analysis was like kind of embedded in proving this, giving an algorithm for this. And because of our improved delta epsilon kind of thing, we actually could shave off like an epsilon to the 4th factor ultimately from prior work. Okay. So it's kind of cool. Like, even though, I shaved off a square root of epsilon in the analysis, like, it kind of builds up more and more. Okay. Yeah. So I thought it was just funny, like, this one comment guy was, yeah, there is no, actually, that's true. I agree. There's no strong algorithmic, mathematical, or theoretical novelty, but I think it's very clean. So I like that. Yeah.
Did the previous epsilon of the 7.4 also use a power method?
Yeah. But they were analyzing in a very different way still. And there were some other losses too. That. Yeah.
For this program, how to get the assumption?
Yeah, so how do you get the assumption, right? So this matrix is an entry-wise non-negative matrix, right? So I can just make sure that error is also entry-wise non-negative by adding a little bit. So that's how I get the assumption. Yeah, so this was a natural setting where this model held true. Like, I could actually compute delta MVPs for this matrix in time that was roughly n to the 1.1, so I didn't write that, over delta squared. So that's kind of where this running times come from, right? You're just running 1 over epsilon times n over epsilon squared. And it was true that the error vector was not negative. I know the top eigenvector has to be non-negative by this thing called the Perron-Frobenius theorem, because the matrix is entry-wise non-negative. But yeah, it is a clean model, and I think we nailed on the right analysis of it. So now let's go back, and it has some interesting Johnson application.
You use exponential parity PST.
Yeah, so this is an input like this is the matrix we care about, and this matrix is PSD.
Yeah,
Yeah.
just wondering why you can't just calculate the L norm. I guess.
You can do the L2 norm squared, it's very
Yeah.
flexible, yeah. But that gives you slightly different. Okay. All right, so now let's go to David's question, right? So what do we show, right? So I'm not in our work, we also show that, right? Okay. I just showed this to you actually. We show power method with roughly 1 over epsilon iterations can already handle epsilon MDPs. Okay, so that's like that was the talk. In the noises setting where I have exact matrix vector products, there are much better algorithms. So they're so-called Krylov subspace-based methods. It's like a fancy name, but essentially what they're doing is by taking very few matrix vector products, only 1 over square root of 1 over epsilon, you can combine them in a very clever way to actually approximate or simulate as if you're doing 1 over epsilon steps. Okay, so these are very nice methods, but we have a lower bound that says, okay, there's very simple examples so that if I have epsilon MDPs, the adversary can easily design a setting where these smarter algorithms will also take 1 over epsilon steps. Okay, so you don't gain anything. And essentially the reason is the way these smarter algorithms are combining matrix vector products is essentially crazy. They're using like a very fancy, Chebyshev polynomial, whose coefficients are like, okay, plus minus whatever, right? There's some subtractions, but well, the lower bound example is very simple, but essentially the high level meta point is like somehow very fine-grained algorithms don't really handle noise, in a nice way, because they are very brittle, right? They're using very special structure to gain some advantage. So if you noise that or add a little bit noise to the structure, then they cannot guarantee some. Yeah.
Is it possible to explain for parallel subspaces what are the stronger assumption for MEPs? Like maybe they don't align with like the top
no, so you kind of always have to do this 1 over epsilon. Yeah. So I have to think, but my guess is no. But maybe there's another way to change the model where you would do gate something. I'm not sure. Okay, so in conclusion, right? My last slide. So we studied a natural setting of matrix vector products that are not exact. The algorithm generating them was like, okay, who knows what the hell's going on? So we just think, okay, it's adversarial. Like they can do, let's just say they can do whatever. Maybe the algorithm had some nicer structure, but okay, we don't know. And the thing I like is like this simple algorithm of power method works and the proof is very clean. And like I said, these complicated but smarter algorithms become slightly less useful, right? If they're already taking 1 over epsilon steps, then why would I like work with Chebyshev polynomials when I don't have to? And maybe at a high level, it's like, if you find that this model is relevant or interesting to you, I would love to chat later. But yeah, that's it. Thanks for being here.
questions. Did you also try their kernel functions?
Yeah, so our thing works for every kernel function you get measured. You get slightly different guarantees. Yeah.
You said something about you take the best one in the last iteration.
Yeah.
Could you also hope to prove that like once you have a good vector, it never becomes too bad?
You can prove that. It turns out if once you have a good vector, sometimes you can go backwards a little bit, but then the next step will go forward. So it's like, you might like jump around a bit. That's why the guarantee is at some point you'll be done, and you can check when you're done actually.
Right.
Well, and then follow up to that, can you actually know like when you already can backmove and which
Not really, because we don't know what lambda1 is, and the algorithm is like doesn't really know what's happening, right? The algorithm is just the power method code, but I'm just giving you the different initial. I like, instead of having the the code function that says compute exact matrix vector product is replacing with delta approximate two-sided products. The algorithm is totally like unaware of what's happening. It's just like doing a bunch of steps and then it's outputting a vector. Maybe one could do that, but we didn't do it.
So this n to the 1.1 is just coming from density.
Yeah.
Is there any worry that like if you get a completely different algorithm for that, then it goes into n that you no longer would use this in a separate game?
No, so the way our algorithm's written is like a black box access to KD. So every time you have KD progress, this will actually give you. So it's not exactly right. You can't really use kernel instance exactly because we have a vector, right? So you get weighted sum. So there needs to be a way to translate that. So this algorithm is actually a black box access to KD. So
Oh, I see.
yeah.
Okay. Thanks, Sandeep.